Right, okay. So to remind us of the definitions and the topics that we discussed in our last class, we'll go over some examples, right? Um, Let me first share my screen with you. Okay. Right, so we usually denote by M sub M cross N of R, the set of M by N matrices. And this set, let me write it, the set of M by N matrices. Now, if it is a square matrix, we will simply put the odd over here without writing M times N. The size of the matrix, we will simply put M sub N. Okay. Where entries are all the entries come from the set of real numbers, right? So this together with matrix addition is a group. This example we have seen for square matrices. When you have a matrix of this size, when you put all these matrices in one set, M by N matrices, this is also a group under matrix addition, right? Let me write is a group under matrix addition. So in order to see that this is in fact a group, we know that associativity, the matrix addition is associative. We have seen this in matrix algebra. What is the identity of this group? The identity of this group?
Zero matrix,
Yeah, zero matrix of size
M by N.
M by N, right? So zero matrix usually denoted by O sub M by N uh, would be our identity, right? And then let's take any matrix A from this set. What is the inverse? Now, the other one, after we check for associativity and identity, we had to see that each and every element in the set has an inverse. What is the inverse of this matrix? Inverse of this matrix?
Minus A.
Minus A, right? We take all entries in A to be negative, they are negative counterparts, which would be simply denoted by negative A. This is also a matrix of the same size. We simply take all the entries to be negative, right? This is the inverse of A, right? So the inverses exist, the identity is there for the group, associativity holds. Therefore, we have seen this in our previous class that this is a group under matrix addition. Now let's consider this one. All n by n matrices where entries come from the set of real numbers. All entries are real, right? This under matrix multiplication. Okay. Is this a group?
Yes.
Okay, you're saying yes, right. Any other different answers? Anybody saying no?
No, madam. There could be instances where the inverse doesn't exist, right?
Okay,
So we cannot.
can you give me an exact example?
Uh,
The answer
some
is correct. This is not a group under matrix multiplication. In that case, we have to provide a counterexample.
square matrix with determinant 0 might.
Okay, so a specific example. What about the zero matrix of order n?
Yeah.
Yeah, so we go with that. Zero matrix of order n. Even though we see the identity is there, which would be the identity matrix of order n, right? Inverses does not exist for all matrices in this set, specifically the matrices which have the determinant to be zero. For the inverse of a matrix, these are all square matrices, right? So we can talk about inverses, at least the existence of it. For the inverse to exist, the determinant must be non-zero. But the zero matrix, we know the determinant of that is 0, right? So this is not a group, since the zero matrix of order n. O sub n, right, is singular. Or we can simply write non-invertible. It's non-invertible. So an inverse for this matrix does not exist. Not all elements in this set have inverses. Therefore, it's not a group, right? Now with this, if I define, going from this example, if we define S to be matrices that are in this set, okay, I'll write it as AN, where AN is an element in Mn of R, a square matrix of order n with real entries, right? Such that the determinant of A is non-zero, right? What about this set now? This set together with matrix multiplication. You have matrices over here, matrix multiplication. Is this a group? Associativity is an inherent property. We have seen this in matrix algebra, right? Multiplication of matrices, it's associative. What about the identity?
This is a group.
This is a group, yes. We do have the identity to be the identity matrix. And for any element that you take from this set, because it is invertible, right? An inverse exists. So the first thing that we have to show in this case is S is closed under multiplication. S is closed under the binary operation multiplication. That is the first thing, right? Because now this is a very specific set we are talking about. We are taking all these matrices with determinant non-zero. So you take any two elements from here, you multiply, you should get an element inside this set. That's the first thing that we have to check. So first, we show that S is closed under matrix multiplication. We show that it's closed under matrix multiplication. Right, so let's take AN, BN, or without having to write AN, we can simply write A and B. Doesn't matter. Two elements in this, right? What can you say about the product? We want to show that AN times BN is an element in S. That's how we prove that it's closed under this given binary operation, multiplication, which is multiplication. Observe that times Bn, which we would simply denote as AN, is defined because they are of the same order and is of the same order. That is the first thing, right? This element that you see must come from here. Not only that, the determinant of this matrix that you see over here must be non-zero if it belongs to this set, right? So observe that this multiplication is in fact an element in the set of matrices of order n with real entries and it's invertible. Why? How do we show that the determinant is non-zero? We simply use properties that we learn in matrix algebra, right? With respect to determinants. What is the determinant of AN, BN? This
The
is
determinants separately can be multiplied.
yeah, so the determinant of the product is the product of the two determinants, right? And then we know this determinant is non-zero, this value that you see over here is non-zero, therefore the product is non-zero. This is because determinant of An is non-zero, determinant of Bn is non-zero, hence the product must be non-zero. Right? These two are elements in S, so they satisfy this condition. Now you see, we have the product be an element in this set. The determinant is non-zero. Therefore, A and Bn is an element in S. We have shown that S is closed under matrix multiplication. Right? We have shown that S is closed under matrix multiplication. And associativity is an inherent property. So associativity holds. The other thing is the identity. Identity is simply the identity matrix IN, identity matrix of order n, right? Which is simply this matrix, right? This is the identity matrix. You take any matrix of the same order. So you take any matrix from this set, take the multiplication by IN on the left or on the right, you would end up getting that element, right? For AN, any element that you take from this set, we know that IN times AN is equal to AN times IN is equal to AN. So IN, the identity matrix of order n, is the identity of this group. And then let's take any element AN from this set S, right? Because the determinant of AN is non-zero, AN is invertible, that is AN inverse exists. It's invertible, so you can find the inverse of the matrix AN. Not only it exists, it satisfies this equation. So we understand for any element that you take from S, because the determinant is non-zero, its inverse exists. So now all axioms are satisfied. We can conclude this is in fact a group. Right? So this is a group. Right. Is this an abelian group?
No,
No. Why is that?
Commutativity does not hold multiplication.
Yeah, multiplication is not commutative always. It's not commutative always. In some instances, yes. For example, over here, these you can commute, you get the same thing, but it's not the case for every pair of matrices that you pick, right? So this group is a group that is not Tauberian. Right? Okay. Now, just to remind us of some of the examples and topics that we went over, I'll ask you a very small question. Is this group a subgroup of this? What do you think?
Because the binary operation is different, this cannot be a subgroup.
Yes, very good. Because the binary operation is different, even though S is a subset of N of R, the binary operation over here is different from the binary operation that you see for this subset, defined on this subset, right? Therefore, it's not a subgroup. If it is a subgroup, it must be a subset and must be a group of its on its own under the same binary operation. Therefore, it's not a subgroup, right? No, because the binary operations are different. Right. Now, why did I pick this example? Because you have seen something related to this one in linear algebra, right? Now, how do we define a linear transformation? It actually has a direct connection to this group that we have just learned. So, this group has a special name, right? This is what we call the general linear group of order n. And usually we denote it by, let me write, and is denoted by general linear group of order n, right? So what does it contain? All invertible n by n matrices with real entries, right? And now, see how this is connected to invertible linear transformations. You take any matrix from here, any element from here. You take any element from here. With this element, I define a function from Rn to Rn. Okay? By T of x equals 8 times x. So this x comes from Rn. It has n coordinates, right? Now, this is what we call an invertible linear transformation. This function is what we call an invertible linear transformation. Right? Now, you see, this is invertible y. You can define T inverse, right? It's a function. So it will be, once again, from Rn to Rn. And we can define this function by taking T inverse of x to be simply A inverse X. Yes, A inverse of X. Right? So we see that matrix multiplication in this case corresponds to composition of linear transformations. Now observe, if I take T composite, T inverse of X, right? What do we have over here? T of T inverse of X. This is equal to what? T of A inverse X. And we know this transformation is defined to be AX. So we have A times A inverse X. What is this? Simply X. X is being mapped to X. Okay? And we can simply write it to be the identity function. Right? On the other hand, we can once again show this composition also at the end gives you this. So now we see that matrix multiplication that you see over here, matrix multiplication has a direct correspondence to composition of linear transformations, right? Even when you take two different transformations and you compose them, right? What you get at the end, right? The end result would be a multiplication of matrices. Now, with all this information, we can define a group taking all these invertible linear transformations, where T is from Rn. I will simply write an invertible linear transformation, so you know it's in this form, where A comes from this set. An invertible linear transformation, right? And not only this, this is a group under function composition. Is a group, and this is actually denoted by is a group. Let me write denoted by simply GL of R without that. Right? So this is also a group. This is a group under function composition. Associativity holds for function composition. We know this, right? And you take any two transformations, any two elements from this set, you compose them together. Take the composite of the two transformations. What you get is an invertible linear transformation, right? An invertible linear transformation. So as an exercise, just show that this is in fact a group, right? I will give it as an as maybe a homework problem. Okay, we see that the identity function is the identity, and then the inverse, you can see how it's defined. So we see out of this group, we have taken some elements of it, defined an invertible linear transformation, put all that in one set, we have another group. Okay, right. If you have any questions, you can ask me. Wait, sorry. Okay. Right. So, okay. Let me give you these two other definitions. Definition of a semigroup, because you might run into these terms as well. Now, semigroup, now we know all these axioms that are given for a group. The group must be closed under its the set must be closed under its given binary operation. Associativity must hold for the binary operation. Identity must be there for every, and a unique identity must be there. For every element, there is a unique inverse. Now, in some instances, for a given, for some sets with just a binary operation, we might not C, then satisfying all three axioms, right? So now a semigroup is a set with an associative binary operation, right? Semigroup is what defined as with an associative binary operation. Right? So in this case, only that first axiom is there that we have taken from a group. We have a set, a binary operation, and it's associative. There is no identity, there are no inverses, right? Not all elements have inverses, maybe. Therefore, we call this a semigroup. Then we have a monoid. Monoid is a semigroup with an identity, right? So this is defined to be a semigroup defined to be a semigroup that has an identity. Okay, can you give me an example of a monoid?
The example that we did not have for the invertibility.
Invertibility, this one. Sorry, this one. Yes, very good. Now in this case, what do we have? We have an identity, the identity matrix, but there is not all elements in the set have inverses. Therefore, it's a monoid. Very good. Right? Now, the other question, what can you say about a group? Is a group a semigroup? If G is a group, can we say that it's a semigroup? And
Yes.
monoid?
Yes.
Yes, very good. Because a group, it has a binary operation, it's associative. So first of all, it's a semigroup. Not only that, it has an identity. Therefore, it's a monoid. And going further, every element in the set has an inverse, right? So we start off with a semigroup, then a monoid, then we get to a group, right? So let me write it. Every group is for the semigroup and a monoid. And a monoid, right? Now some more examples on subgroups. Mm, Right, let's consider this. Consider this group, right? I'll write all the elements in this. We have 0, 1, 2, up to 9. This is a group under addition modulo 10, right? I will not write, once you know what the binary operation is on a given set, you don't have to write it using this form, right? I will simply denote the group by this set. Okay, right. Now, is H, which is given by, let's say, 0 and 5, a subgroup of Z10. So we understand H also has the same binary operation defined on it. Okay, so is this a subgroup of Z10? Is it a subgroup of this given group? identity is there, right? You take 0, its inverse is 0. 0 is the identity. What is the inverse of 5?
5.
Yeah, inverse of 5 is 5 itself. Is it closed under the given binary operation?
Yes.
Yes, it's closed under the given binary operation, right? If you add 5 to itself and take modulo 10, that means 5 plus 5, which is 10, divide by 10, take the remainder, you have 0. You add 5, because you see, adding these two, we definitely get 5, which is in there, right? Adding modulo 10, that is. Now, if I take add 5 to itself 2 times, right? The addition gives you 15. Divide by 10, take the remainder, you have 5. So no matter what, let me write it in words. Associativity is an inherent property, right? So we can simply write associativity is inherent. And then the identity is in there. The identity of the group is 0 and 0 is in there. And inverse of 0 is 0. Inverse of 5 is 5, both of which are in this set H, right? And then if I take 5 raised to the power of n, right? For any n integer, we have what? And we do this addition n times, right? Divided by 10, take the remainder. This is either 0 or 5. Why do we have that? Because any multiple of 5 will always be divisible by 5 or 10, right? So the remainders will either be 0 if it's divisible by 10 or simply 5, right? Therefore, we see that H is closed under this binary operation as well, right? Therefore, we can conclude and write H is a subgroup of this. Okay.
Madam,
Yeah.
can you explain again what you did that 5 to the power n thing and the later part?
This one. Okay. Now, when we have to check whether the set is closed under the given binary operation, right? We have to check by simply taking that element and adding the element to itself as well, right? Why do I say this? Now, in this other, I will come back to this one, right? In this other example, I'll write it as n maybe. Let's go with, I don't know, let's go with 4, right? A subgroup. Okay. Is this a subgroup?
No.
No. First of all, the inverse for 4 is not in there, right? Not only that, usually what is the first thing that we check? We check whether this is closed under the given binary operation. Now, when you see that the inverse doesn't exist, you can simply write that, you can simply give that justification and conclude this is not a subgroup, right? But on the other hand, if you are simply asked to check, now that is because I'm asking you to check whether this is a subgroup. If I ask you to check whether n is closed under the given binary operation, right? If I word it this way, is n closed under addition modulo 10, the same binary operation that's defined for this particular group. Is it closed under this binary operation? The answer is no. Why? Certainly, when you add these two elements, you get 4. Divided by 10, you get the remainder 4. you add 0 to itself because uh, when you check whether it's closed under the given binary operation, you have to check it for any pair of elements that you take from the set. Any pair of elements, right? So 0, 0 is an element in n cross n. If you remember the definition of a binary operation. 4, 4 on the other hand is also an element in the product n cross n, right? So you take any pair of elements in this set. Now in this case, what I'm going to do is I will take 4 and once again 4 and apply the binary operation to these two elements. What do we get? 4 plus 4 is 8. Divide by 10, take the remainder. You have 8. But 8 is not an element in n, right? Therefore, n is not closed under this binary operation. Now, why did I do this? To check whether this is closed under this given binary operation. That is actually the first thing that we have to check, right? Now, obviously, when you add 0 and 5 together under this binary operation, what you get is 5. You add 0 to itself n times. It doesn't really matter for any positive integer n, positive or negative, right? What do we get? 0. But when it comes to 5, you add 5 to itself. What do you get under this binary operation? It's 0. 5 plus 5 plus 5 would end up being 5. Once again, an element in this set, right? So we only have to worry about powers of 5 with respect to this set. It has only two elements. One is the identity, the other one is the non-trivial element. Right, so any power of this element, no matter how many times we add that element to itself, you will simply get 0 or 5 existing elements in the set. With this, we conclude it's closed under the given binary operation. Is it clear?
Madam, I'm not quite getting that 5 to the power n thing. Why do we have to get the n power since now since we are doing this plus 10 operation, shouldn't we add this one 10 times to itself if we are taking elements from the set H?
Say it again, and shouldn't
So,
we add it?
since we are considering plus 10, that means addition modulo 10, right?
Yeah.
Don't we have to like uh, add the element to itself 10 times
Why,
we
why,
are
why 10 times?
because we are using addition modulo 10, or just what we are considering is we are adding the all elements together and dividing by 10 and getting the modulo.
No, this is just for one element we are doing. Why? This is the non-trivial element. Okay, you're saying 10 because it's addition modulo 10. If you go back to this example, now in this case, it's either 0 or 5 anyway, because you take any multiple of 5, will always be divisible by 5. In some cases, divisible by 10. When it's divisible by 10, you have the remainder 0. In every other instance, remainder 5. When it comes to this example, right, you add 4 to 4, 8. 4 plus 4 plus 4, modulo 10, you get 2. You add 4 plus 4 plus 4 times, what do we get?
6.
6. Likewise, you get different answers. So we are writing this for the generic case, no matter how many, because if you take, this is a finite set. So any power of 5 must be in there, right? Any power of 5, if you're not sure that this is closed under the binary operation, forget about this set. If you look at this one, any power of 5 must be in there because it's a group, right? So any power of 5 is an element. We have to consider that element as well together with 5 or any other element and show that any power of 5 also is in there. To conclude, it's closed under the given binary operation. It's not just 10. This is for the generic case we are writing. I mean, when you see that the remainder gives you 0 or 5, you don't even have to write this many. You can simply write any, you add 5 to itself any number of times. You have a multiple of 5, which will always be divisible by 5. In some instances, divisible by 10, right? So when it's divisible by 10, the remainder for this particular binary operation will be 0. In any other case, 5. Do you
But
get this part?
yeah, I get that part, madam. Now, when we consider the set H, the only possible values, if we do that modulo thing, would be if we pick only two elements from that at once, right? We are not going to pick multiple elements at the same time, are we?
No, we are not going to pick multiple elements.
So that means we are picking either 0 and 5 from it, or 5 and 5 from it, or 0 and 0 from it, right?
Yes.
So isn't it sufficient for us to check only up to maybe 10, because that is the maximum value we are getting from this specific case?
Maximum value. In that case, you can only go for the 3 cases and write. In that case, you only have to write the 3 cases, 0 plus 0, 5 plus 5, or 0 plus 5. That is
Yeah.
also sufficient. But this is we are writing for the generic case, not just for this example. Not just for this example. This is, I'm just trying to show you, this is how we write. For any other, say you have Z 100, right? Uh, Obviously, we are not going to, once you understand a small group, that is sufficient to think about any other larger group, right? And you take a subgroup with enough elements, let's say 50 or so, right? Then how are we going to, we have to go for the general case, right? This is one way to think about it. But for this case, what you're saying is right, you don't even have to go up to 10. You just simply write uh, 0 plus 0. 0. 5 plus 5. 0. 0 plus 5. Sorry, 5.
Okay, got it, madam. Now I got it.
Okay, right.
Yeah.
Right. Any other question? Okay, now that we have done something like this, let's go over this definition also. I'll give it right here itself. Okay, let's take G to be a group. Under the binary operation star, right? And let's take n to be positive. And n be positive. Now, by convention, no, let's take A in G will first of all, A be an element in G. By convention, we let A raised to the power of 0, A0, I will simply say A0, to be E, the identity of G. Identity of G, right? And then AN will be defined as A star, applying the binary operation on n terms of A. Right? So if you take A inverse n times like this, because it's associative, it's a group, the binary operation is associative, you can disregard you can disregard writing parentheses, right? This will be A inverse n times, right? And we can simply write this as negative n, right? So we see the usual and with this notation, we see that if we take A m times star A n times, this would simply be A m plus n. So usual law of exponents would work on this case. It works on this. Okay? Usual. Right, so you can do this one. Right. Now, if you go to the group Z, right? Now, when I simply write Z, we understand the binary operation is addition. Okay? What is 1 squared? Sorry, 1 squared?
When the binary operation is addition, that should be 2, right?
Yes, exactly. This is 2. Why? This is, if you refer to this one, this is simply not the multiplication that we know, because the binary operation defined on this set is plus addition. This is 1 plus 1, right? 1 cube would simply be 3, like this, right? Now, if we go with this group, no, let's go with Z5. 4 squared would simply be what? 4, addition modulo of 5, 4. This will simply be 3. Right, so we understand the use of exponents in this case. Okay, do you all have any questions? Okay, now, so for Z10, let's take all possible subgroups, okay? Let me write list of subgroups of Z10. We first of all have the trivial subgroup containing only the identity of the set, identity of the group. Then we have 0, 5 as we have seen earlier. Then we have this one, 0, 2, 4, 6, and 8. Right? Then we have the group itself. These are 1, 2, 3, 4. We have 4. Yes. These are all the possible subgroups of Z10. Right? And then we can represent all these in a subgroup diagram. How do we get a subgroup diagram? Right? We start off with the group. From the group, we take a straight line down to all these subgroups. Now, none of these are, only this is a subgroup, only this is a subset of this and this, but this is not a subset of this given set. Therefore, we have to draw them separately. One would come here. And then another line should go to 0, 5, right? And then this other subgroup, right? We simply don't take the trivial subgroup over here and take a line connecting Z10 to this one. This is because this is a subgroup of this and this as well. So that is how it's a subgroup diagram. All these subgroups are listed over here, right? Now, if you take Z5, we have the subgroups, the trivial one and Z5. Those are the only subgroups for this particular group. So the diagram would be subgroup diagram would be, we start off with the group, and any subgroup, every subgroup will be listed down, right? And it will be connected, because we only have the trivial one, this is now directly connected to this one. No other subgroup in between. How do we actually know to find these subgroups? There is a theorem which you will learn Lagrange's theorem. This says when the given group is finite, in both cases, you see, the groups are finite, right? Then any subgroup, right? You take any subgroup, the order of the subgroup must divide the order of the group. What do we mean by the order of the group? The number of elements in it, right? So if you go to this one, we will come back to these examples when we talk about Lagrange's theorem, right? Z10, it has 10 elements, right? So 10 is divisible by 1, 10, 2, and 5. See, we have subgroups, one subgroup containing one element, another one containing two elements, another one containing 5 elements, another one containing 10 elements, right? When it comes to 5, a prime number only divisible by 1 and 5. So we have two subgroups, the trivial one and the group itself. Okay, right. Now, before we get to the subgroup criterion, let me write this one theorem. Let's take G to be a group and H to be a subset of G, right? We say that H is a subgroup of G if and only if. First condition is it must be closed under the given binary operation, right? H must be under the binary operation on G. I'll take the binary operation, yeah, star on G. Second condition, it must have the identity. E of G must also be in H, right? The other one is for any A in H, A inverse must also be in H, right? In other words, it actually must be a group on its own. Now, this seems very trivial, right? It's an if and only if statement. So first we have to suppose that H is a subgroup, then all these conditions are met by definition of a group. If H is a subgroup of G, obviously it's a group on its own under the same binary operation. Therefore, all three conditions are met. On the other hand, if all three conditions are met, H must be a subgroup. Can we simply deduce that by just looking at this? Yes, H is a subgroup of G. Seems like all conditions are there, right? For it to be a group, but one is missing. One axiom is missing. And what is that? Associativity of the binary operation, isn't it? But you see, associativity is also inherent in this case. Why? You take any three elements A, B, C from H, because H is a subset of G. A, B, C are elements in G as well. So if I put star over here, this binary operation is associative on G. Therefore, it must be associative on H, because this equation is valid if we simply look at G and the binary operation and all these elements as being in G. They are in G. Okay, so associativity is inherent. Right, now we write the subgroup criteria. This is a criteria to check that a given set is a subgroup, a given set, which is a subset of a group, is in fact a subgroup, right? So let me write subgroup criteria, right? Let's take G to be a group. And let's take H to be a subset of G. H to be a non-empty subset of G. I'll just write such that H is not empty, right? Then we say that H is a subgroup of G if and only if for any AB that you take from H, we have A star B inverse to be in H. So if you are asked to find that a given subset is in fact a subgroup, all you have to do is use this criterion. First, you have to show that it's not empty and it satisfies this given condition. Now we have to prove this and we will do it together. If H is a subgroup of G, do we have this condition to be satisfied? Do we have this condition to be satisfied if H is a subgroup of G? Yes, it is, right? Why? You take any two elements from H. Now, H is a subgroup. In other words, it's a group on its own under the same binary operation as G, which is defined on G. Therefore, B inverse is also an element in H. H is a subgroup that is closed under the binary operation star. So we have two elements, A and B inverse in H. It's closed under the binary operation, so we must have A star B inverse to be in there. Right? Right. Now we can pick these two elements from H because we are given that H is non-empty. Right? Let A be in H because I'll write H is not empty. It has to be not empty, right? H is a group. And so B inverse must also be an element in H. And H is closed under star, so that we must have A star B inverse to be in H. A is taken from H. We see that B inverse is also an element in H, so that A star B inverse must be in H, right? This is because it's a group. That's the supposition. Now, the condition holds. Why? Because we have chosen A and B arbitrarily. That means this should work for any and every element that you pick from the set. So we can write to formally conclude this part. Since A and B are chosen arbitrarily, we have for all AB in H, AB inverse to be in H, right? Now, on the other hand, if this condition is satisfied, we had to show that H is a subgroup of G, right? Conversely, let's suppose for all AB in H, we have A star B inverse to be an element in H, right? Conversely, suppose that this statement is true. Now we have to show that H is a subgroup of G. H is given to be not empty. What is the first thing that we have to check? If we go back to this, H must be closed under the given binary operation star, right? So that is the first thing that we check. I'll take this statement to be 1, right? Our supposition. Right. To see that H is closed under the given binary operation, we pick arbitrary elements, two arbitrary elements from H. So let X, Y be chosen arbitrarily from H. We need to show that Okay, how do we show this one? How do we utilize this? Now, to actually utilize this given, it's a position given 1 over here, we will have to first prove something. So I will leave this part over here and first show that the identity is there, and for any element, the inverse is in there. That is what we have to take. If we know that the inverse is also in H, for any given element, if the inverse is in there, if we know y inverse is in there, what we are going to do is simply in this statement 1, we take B to be y inverse. Then obviously we are going to have an A to be X. We have X star or X, I will simply say times, X times the inverse of y inverse, which is y, right? So we have XY to be in H. Before we actually get to this part, we have to show that the inverse is in there. So I'll leave it at that. Go to the other one. We have to show that it doesn't have to be in this order. It doesn't have to be in this order. Let's first show that the identity is in there. For any element, the inverse is in there. Then we'll come back to this one. Right? Okay. Now, associativity, as we have seen before, it's inherent, right? That's why it's not even listed over here. You don't even have to show associativity holes. Only these three. Right. So the first one, to show that the identity is in there. Is in H. How do we utilize this condition? Let's take an element A from this. I'll do the first one, then we'll think about the other one together, okay? Let X be an element in H, right? Now, X is an element in H. What I'm going to do is, in 1, I will take A to be X, B also to be X, right? Because this is true for any AB values in, any AB elements in H, right? So what we do is, um, okay, right. Now, what are we going to do? In 1, I will take A to be X, B to be X, right? Then what do we have? Then we have A times B inverse. So in our case, X times or X star, X inverse, which is what? The identity by definition, right? And this to be an element in H. From that, we have shown that the identity is in fact an element in H. Is it clear to you? So the identity is in there, right? Now, to show for any element the inverse exists, let's take any element from the set H. You can actually consider this X and simply go from there. You don't even have to write this part. But we will do them separately to fully understand what's happening. Okay, let Y be an element in H to show that Y inverse belongs in H. What do we do have to, what do we have to do in this case? How do we utilize 1? How do we use 1 in this case? The given supposition. How do we use 1? Any ideas? Anybody?
1 and y inverse 1 and y is in each, then 1 star y inverse is equal to y.
1
Uh,
star. Ah, you
y
mean
inverse
the identity.
y inverse.
Identity. Okay.
No, madam. 1 star y inverse is equal to y inverse.
Yeah. One meaning the identity.
Yes, madam.
Ah, okay. Yes, very good. So what do we do now? From this first step, in this first step, we have shown that E is in H, and we have arbitrarily chosen Y to be an Y is arbitrarily chosen from H. Now we have two elements. One is E, proven over here. Y is in there. So what do we do? In 1, to show that Y inverse is an element in H, in 1, we take A to be E and B to be Y. Let's take A to be E and B to be Y. Then we have for any AB in H, Y and the identity are in H, right? Y is chosen arbitrarily, E proven. So we take A to be E, B to be Y. We must have E times B inverse, in this case Y inverse, which by definition of the identity is simply Y inverse to be in H. Since Y is chosen arbitrarily, for every element in the set, there is an inverse in H. Okay, so that condition is also satisfied. Do you all have any questions on that? Now we go back to this one to show that H is in fact closed under the given binary operation. Okay, now coming back to show that H is closed under star. Let's take X, Y to be elements in H. Then we have Y inverse to be an element in H. This is proven above. To show that the product XY or X star Y is in H, in 1, we take A to be X and B to be Y inverse. So we have A star B, which is equal to what? Sorry, A star B inverse, which is X star inverse of Y inverse. So the inverse of the inverse, we know the element itself. So we've got X star Y to be an element in H. This is all by 1. So we conclude that, and from this we understand H is closed under the binary operation. We conclude that H is a subgroup of G because it has satisfied all conditions that are listed in this theorem. Okay. Right. Any question? Do you all have any questions? Was it all clear? We'll do a few examples to see how we use the subgroup criterion, okay? Okay. Be a group and let's fix an element G in this, right? Then let's define this set. I will simply call it NG. You will encounter these sets once again, okay? X in G, XG is equal to GX. Okay, now we are going to show that this NG is a subgroup of G. How do we do that? By using the subgroup criterion, right? We will use the subgroup criterion to show that NG is a subgroup of G, right? If I write the subgroup criterion over here, H is a subset of G, where G is a group, okay? I'm not writing it. G is a group, H is a subset of G. H is not empty. Then H is a subgroup of G, if and only if for every AB that you take from H, we must have AB inverse, A star B inverse in H. This is the subgroup criterion. Right. Now to use this, first of all, we have to see that NG is a subset of G. Clearly, it's a subset of G. Why? All these elements are taken from G under satisfying a certain condition, right? So NG is clearly a subset of G. Clearly a subset of G. And the second thing is we have to show that it's not empty. That means you have to at least show a specific element exists in the set. How do we show that it's not empty? Can we find a specific X, a specific element in G satisfying this condition?
The identity is in NG.
How is the identity in there?
The identity is A star J is equal G star A is
Yes.
equal to G.
Yes, very good. So now I have to say I have simply written xg equals gx. This actually has to be written as, by disregarding this star, x star g equals g star x. This is simply x star g. Xg is simply x star g. Okay? X star g. Yes, very good. So the identity is in there. This set is not empty, right? So we can write, observe that for G in G and the identity E in G, we have, by definition, G star E to equal E star G, which equals G, that is something else, but we have this equation so that E is an element satisfying this equation, which is that you see over here. Therefore, E has to be an element in the set N sub G, right? So that E is an element in NG. Okay, therefore, NG is not empty. Right? Now, we are going to show that to prove that NG is a subgroup of G, we will show that for any two elements that you pick from this set, this condition is satisfied, right? Now, let's go with AB in NG, right? We need, because this is an if and only if statement, if this statement is satisfied, if what you see over here is satisfied, we simply conclude H is a subgroup of G. In this case, NG is a subgroup of G. we need to show that A star B inverse is in NG. This is what we have to show. So, in other words, if this element is in NG, that means this element must satisfy this given equation for a fixed G, right? In other words, if this belongs in G, you have to show that A star B inverse star G is equal to G star A star B inverse. If we can show this equation is satisfied, we can conclude A star B inverse is in NG, right? Because why is that? A and B are taken from NG, N sub G really, I'll just call it NG. Because NG is a subset of G, these two elements belong to G as well, right? These two elements belong to G as well. G is a group. So B inverse exists and it is an element in G. It's closed under the given binary operation. So we know that A star B inverse is also an element in G. So we already know that this element is in G. We just have to show this element satisfies this given equation. To conclude, it belongs in the given set. Okay. As a remark, I'll put it over here. Remark. A, B are in G as well. Since NG is a subset of G. Therefore, B inverse belongs in G because G is a group. And A star B inverse is also an element in G. We only have to check for this equation now. Do you have any questions up to this point? Okay. Now what to show that this equation is satisfied? We are taking elements A and B from NG. So those two elements must satisfy this given equation because they belong in the set NG, right? Since, so I can write, since A, B are in NG, we must have AG to equal GA and G to equal GA and BG to equal GB. Okay, those two equations must be satisfied. Okay, right. Now observe, in this equation, we have a B inverse. So what are we going to do? What are we going to do in this case? Using this equation, we will derive another equation for B inverse as well. Okay. Why do we do that? If we do a little bit of rough work, okay? Take a look at this equation. Now, this is a little bit of rough work, not really a part of the proof, okay? I will disregard writing the star in this case. When you see AB inverse, this simply means A star B inverse, okay? AB inverse G, we start with this one. Because star is associated, the binary operation is associative, we can write what? A, B inverse G. Now, instead of B inverse over here, if we had BG, we can simply go back to this equation. Because BG is equal to GB, we can replace BG by G times B. But now we have B inverse G. If we had B inverse G equal G times B inverse. We can simply replace this term by G B inverse. We want to somehow get to this part. Okay. Now, using associativity, we have this one. AG we know is equal to G times A. Now, what do we have by associativity? Exactly what we want, right? So, this is why our first step would be to derive this equation. Okay, so coming back to the proof, we start off with BG equals GB. From this equation, how can we get to this one? Anybody? How can we go to this equation from this is we do have this. We have chosen B to be an element in the set NG, right? So from here, how can we get this equation? If because if when we have this equation, it's simply a matter of manipulating these terms, using these equations, using associativity, simply to derive this equation. But we need to have B inverse G equals GB. Anybody? How do we go from here to here?
Take B inverse in both sides.
Yes, that's a very good start, right? Take B inverse on both sides. What do we have? From this we have B inverse equals B. Now first we take B inverse on the left, right? Using the associativity property over here, we see that B inverse B gives you the identity. Identity times G is simply G. We have B inverse G, once again using associative property over here, this element. Now take B inverse on the right. So we've got B times B inverse is the identity. Identity times any element, that element. Okay. Now with this equation, we go back to, we simply write this one, right? So we start off with A star B inverse is equal to what? Associativity yields, from using associativity, we've got this associativity. This is equal to B inverse star G from this equation is equal to GB inverse, G star B inverse. Now using associativity again, we have this. A star G is simply G star A that you get from this equation. Now using associativity, we see that G star, we can write it like this. Now you see, we have an element A star B inverse, an element in G. We have chosen AB from NG, right? Now, the two elements, A, B are in G, and they satisfy this equation. So by definition of the set NG, it must belong to G. Okay. I will write it on the other side. So we can write must belong in NG, and by the subgroup criterion, we have NG to be a subgroup of Okay. Sorry, is it clear to you? Do you all have any questions? Right. Okay. Let's do one more problem where we use the subgroup criterion. Okay, this is actually given in text as well. Let's take G star to be a group. And let's take A to be once again fixed in G. And we define H to be all powers of A. Show that H is a subgroup of G. Okay. Is it a subset of G? First thing is we have to show that it's a subset of G. It's not empty. After that only we go to that condition in the subgroup criteria. Is it a subset of G? It is a subset, isn't it? Because A is an element in G. Any power of A must belong in G. So all elements that you see in here are elements in G. Therefore, H is a subset of G, right? So we can write clearly H is a subset of G. Is it not empty? How can we show that it's not empty? Anybody? We have to show at least one element exists to prove that it's not empty.
A to the power 1 is equal to A. Since A is in G, then A is in H.
Okay, n equals 1, you're saying. A specific element. How about the identity? Can we show that the identity is in there? That is actually very good, okay? You take n equals 1, A is an element in G, it's in there. But how can we show the identity also is in there? A is already an element in G. Therefore, it's an existing element. It is also in H, right? How can we show the identity is in there?
N equals 0.
Yes, n equals 0, right? When you take the 0th power, you get A raised to the power of 0 is the identity. That's how we have defined these things. And it belongs in H as well. Right. But let's go with this one, what you said. Right. Now what? Now we know that H is not empty. Now to prove to use the subgroup criterion, what is the first step? To use the subgroup criterion, what is the first step? Right. So to use the subgroup criterion, what is the first step? To pick any two elements from H. We arbitrarily pick two elements from H. So let's take X and Y to be elements in H, right? Be two elements in H. We need to show that what do we have to show? We have to show that X star Y inverse is also in H, right? If this element is in H, right, it has to be of the form A raised to some power, because those are the types of elements that are in this set, right? Those are the types of elements that you see in that set. This means, so I will write it, this means we have to show for some M in Z, X star Y inverse is actually equal to A raised to the power of X. This is what we have to show in order to prove that this element belongs in the set H. Okay. Now, X and Y are elements in H. They also must take this same form, right? So we can write, since X and Y are in H, there exists integers R and S such that X is equal to A raised to the power of, let's say, R, and Y is equal to A raised to the power of S. Right? We do have this one. Okay. Now from here, how can we get to this one? Now observe, once again, let's do a little bit of rough work, right? Before we enter into the actual proof. X is A raised to the power of R, right? So when I take X star Y inverse, X can be replaced by AR star Y inverse. Now we know for Y can be written as A raised to the power of S. If Y inverse also can be written as, now you will see, we can actually show that Y, sorry, Y inverse is in fact A raised to the power of negative S. And we know that the usual exponent laws work. Therefore, this ends up being A R plus negative S, R minus S. And for any two integers R and S, R minus S is also an integer. Therefore, this element that you see is an element in H, and this is equal to X star Y inverse. This is exactly what we are supposed to do, right? This is exactly what we have to do. So how do we, now the only thing that we have to do is show that Y inverse is equal to this value over here. How do we do that? Obviously, we will have to use this, right? From that, how do we do that? We have Y equals this is equal to A star, how many times? A times, right? What am I going to do in this case? I'm going to take A inverse on both sides, right? So we have Y star A inverse equal, and now over here we have S A terms, right? And this ends up being the identity. So we have Y star A inverse A raised to the power of what? S minus 1. Okay, A raised to the power of S minus 1. Now what do we do? You can actually do this in the same step as well. We simply take the inverse of A, S minus 1 times on both sides. Right? The inverse of A, S minus 1 times on both sides of the equation. So we have S minus 1, many A inverses popping up on this side. Star with this A minus, A inverse. We've got A inverse of S many A inverses, right? And on this side we have the identity. And now what do? We take Y inverse on the left on both sides. We've got Y inverse, Y. So we end up getting this equation. Right? Now, you don't even have to go doing this part. This is, I have given this so that you understand this part, okay? How we actually get to this one. Here, from here, you can directly come to this step. What do? On both sides, we take A inverse S many times, okay? So from here, you can directly come to this part. Then you take Y inverse on both sides to end up with the required equation. Do you have any questions so far? Now we simply write this. Now we have X star Y inverse to be AR star A negative S, and this simply works out as this. And for integers R and S, we have their difference, R minus S, to be an integer as well, so that A raised to the power R minus S, which is actually equal to X star Y inverse, is in fact an element in H. By subgroup criterion, H is a subgroup of G. Okay, is it clear up to this point? Do you have any questions? Right. Shall we do one more problem where we use the subgroup criterion, or let's go to talk about orders, order of the group and order of the element?
It is better if we could do another problem, madam.
Another problem? Okay. How about we take, okay, let's do this one. Let G be a group, and let's define H to be this. Where x squared, x are all taken from G such that x squared is equal to E. Let me see. Oh, and G has to be abelian. Let G be an abelian group. Otherwise count an abelian group. Okay. Right. Show that H is a subgroup of G. Right. Once again, what is the first step in using the subgroup criterion? We have to show that H is a subset and it is not empty. Then only we go to that condition. Okay. Clearly, H is a subset of G because here all these elements are taken from G. Right? Any element that you take from H belongs to G by definition of H. So we can write clearly H is a subset of G. This is because any element that you take from H, that element is in G by definition of H, right? And then to show that H is not empty, observe that now, let's try and do this together. We have to show at least one element belongs in this set. That means there is at least one element in the set, in the group G, such that when you square that element, you get the identity of the group. Can we think of an element in G satisfying this condition? We only need one element to prove that it's not empty.
Identity itself,
I'm sorry?
we can take the identity.
Exactly, right? Very good. So we take the identity. We observe that identity, you raise it to any power. You take any power of the identity, you get the identity, right? So we know, so that this belongs to H. Observe that. We have to write for E in G. E squared is equal to E, where E is the identity in the usual notation, so that E belongs in H because it satisfies this condition. So we know that H is a subset of G. It's not empty. Now to use the subgroup criterion, we pick any two arbitrary elements from H. So let's take X and Y to be elements in H. We need to show that we have to show that X star Y inverse belongs in H. In other words, it has to satisfy this equation. In other words, X star Y inverse squared must equal E. Now, we have picked X and Y from H. What can we say about those two elements if they're taken from H? We have to use that as well in order to show that this ends up being the identity. Since X and Y belong in H, what do we have? If you go to the set, any element that you take from this set must satisfy this condition. That's how the elements are picked, right? Because X and Y are in H, we must have X squared to equal E and Y squared to equal the identity of the group, right? So we do have that. Now observe, if you go to this equation that you must show will be satisfied, you have to work out something for Y inverse as well, which we will get from this equation, right? Once again, this is sort of like rougher. It's better to do this so that you know where you actually have to go, right? If you look at this equation, this means we can write as X squared star Y inverse square, right? With this, we can, if we know the square of Y inverse is equal to the identity, this is given to be the identity. We have identity times identity, which is simply the identity. So what do we have to show? We have to show that Y inverse square is the identity. That's all we have to show. And to show this, we will use this equation. Now, okay, can can you tell me where we have used the fact that G is an abelian group?
So that we can say that y square would be y star y inverse and inverse star y.
That is actually the definition of the inverse. It will definitely work for any inverse with it with the element, right? The element and the corresponding inverse. Where have we used it? Okay, keep that question in mind. Let's first prove this one, and when we actually get back to that one, I'll ask it again. Right, okay. So this is like rough work, okay? Now we see what we have to do. We have y squared is equal to the identity. How do we go from here to this one? This implies y star y is equal to E. What do? We take y inverse on the left or in the right on both sides, right? So go on the left. This gives you the identity times y. Y inverse, the identity is simply y inverse. So we have y equals to y inverse, right? Y equals y inverse. Y squared is equal to the identity because y is equal to its inverse. We have y inverse squared also equal to the identity. Or you can simply take y inverse once again in this equation on both sides to see that on the left you get the identity, on the right you get the square of y inverse. That also would work. Okay, so we have this equation. Now let's go to this one. No, let me simply start with x star y inverse square, right? Now observe x, y, they are both taken from H. H is a subset of G. Therefore, those two elements must belong in G. Y inverse must belong in G. G is a group. And so x star y inverse must be an element in G. So we understand this is an element in G. We only need to check whether it belongs to H by ensuring this equation is satisfied. Okay, or at least looking at the equation. Now this is equal to, I said, x squared times, or put it in red balloons, x squared star y inverse square. Right. Why can we use this? Why is this equal to this one? Because if you look at it, if you sort of factor it out, what you see is x star y inverse star, because you're taking the square of this element, x star y inverse. From this, how can you conclude it's equal to x squared star the square of y inverse?
Since G is an abelian group, we can take y inverse star x is equal to x star y inverse.
Exactly. This is where we use the fact that G is abelian. So that you commute these, you are able to commute these two elements, right? So we can write x star y inverse, and this you can write x star y inverse, commuting these two elements, because we can do that. These two elements are elements in G, and G is abelian. This is where we use that property. Now, once again, using associativity, we can write x star x. This is what? X squared y inverse square. From this equation and this one, we see that It's the identity squared, which is simply the identity. Okay. Therefore, X star Y inverse belongs in NG, and by the subgroup criterion, subgroup of G. Is it clear? What questions do you have? Okay, then shall we move to the order of the set and the order of an element? Order of the group, I mean to say. Order of a group. Okay, so what do we mean by the order of a group? If you are given a group G, right? It might have a finite number of elements or an infinite number of elements. If it has only a finite number of elements, say n, the order of the group is defined to be the number of elements, in that case n. If it is infinite, for example, like Z together with addition, right? Then the order of that group is said to be infinity. So let me write. If a group has n elements, then its order. This is denoted by, I will put it right here, denoted by is said to be n. Right? And if G has infinitely many elements, then the order of G is said to be infinity. Similarly, we can define the order for an element in a group as well. So let me write order of an element. Let G be a group, and let's take any element A in G, right? If now the order of A we define by, let me write it with first. If there exists a positive integer n, n is positive, it's an integer, so it's a counting now. Positive integer n such that an raised to the n power is the identity of the group E, right? If we can find n satisfying this equation for this element A, then the least such n, the least value of n satisfying this equation for the element A is what we call the order of that element, right? So we can write then the least such n. Order of A, and we denote it by okay, and on the other hand, if no such n exists, if you can't find such n satisfying this equation for a given element, we say that the order is infinite, right? So let me write, if no such n exists, we write order of A to be infinity, right? And one thing to be observed, oh, okay. What is the, let G be any group in the usual notation, let's take E to be the identity. What is the order of the identity? Order of the identity.
1.
Sorry?
1.
1, yes, 1, right? Now if G is any group, with identity E, we know that the order of E is 1. This is because E raised to power 1 is simply E, the identity. Now observe, when you take E squared, you get E. E cube also, you get the identity. But to define the order, we only have to take the least, the smallest n, satisfying this equation. And if you look at all this, the smallest n ends up being 1. So order of the identity is simply 1. Okay, right. Okay, let's do this example. Let's take the group Z, right? In this group, what is the order of? What is the order of? Let's take any integer. What is the order of 1? What is the order of 1? First, we must identify the identity of the group. Identity in this group is what? 0, because Z is a group under addition. Okay, identity is 0. So for what power of 1 do we get? Let me write, do we have n such that? Do we have positive n? This is positive, okay? N such that 1 raised to power n ends up being the identity. Do we have such n? Now n is a positive number. If we take n equals 1, that is the first number, right? The smallest number, smallest positive number is 1, positive integer. 1 raised to the power of 1 is simply 1. 1 squared, 1 raised to the power of 1 is 1. 1 squared is what? 1 plus 1, which is 2. If you take 1 cube, we have 1 plus 1 plus 1, which is 3. So for what positive n do we have this equation to be satisfied? Anybody? For no n, right? No such n would exist. No matter how many times you add 1 to itself, you will never get to 0. So no such n exists. In this case, the order of one is infinity. Sorry, the order of one is infinity. Okay. Is it clear to you? Do you all have any questions? Tell me the order of -1 in this group, Z under addition.
Infinity.
Yes, this is also infinity, right? Why? No matter how many times you take -1 raised to the power of 1. This is -1. -1 square. This would be -1 plus -1, -2, right? You take -1 cube, you get -3. No matter which n you take, right? This will never be 0. It will simply be -n. It will never go to 0. So no such n exists. The order of this value, order of this integer -1 will also be infinity. Okay, right. Let's take a look at this example. Let's take R, non-zero R's. Let's denote it by this. Non-zero reals, okay? The set of non-zero real numbers. What is the identity of this set? This group? What is the identity of the group?
One.
Identity is 1. So E is 1. What is the order of 1? Since it is the identity, it is 1. Order of -1?
Two.
2. Exactly. You take -1 square, -1 times -1, you get 1. Order of 3?
Infinity.
Infinity. Order of -5, let's say.
It's also infinity.
This is also infinity. So we see you take any element from this set that is not 1 or -1. The order will be infinite. The only finite orders we see for elements in this set would be for 1 and -1. That's it. For any other element in the set, the order will be infinite. Okay, right. Now, let's take a look at this example. Okay, we have done this several times now. So let's take the same set. Z10, binary operation, addition modulo 10, right? Okay, what is the identity of this set? It is 0, right? Before we even find orders of any element, right? Can we have an element of infinite order in this set? Can we have an element of infinite order in this set? Before we even start to find orders of these elements, I can say every element must have finite order. Why is that? We definitely don't have an element of infinite order for this particular set. Why is that? Okay, that is something that you have to think about. And during our next class, I will ask the question again. And I will also include it in our homework set, right? I'll give you a small hint. This is a finite set, right? It's a finite set, right? Now, what is the order of 1? So first of all, we know the order of 0 is simply 1. What is the order of 1? We add 1 to itself. You have 2. Modulo 10, you get 2, not 0. How many times should we add 1 to get 0?
10.
10, yes, very good. So order is 10. Now observe, if we add 1 20 times, we would still get the identity element 0. But the order is defined so that we pick the smallest integer satisfying the given equation. This 1 raised to the power of n, which I have replaced by 10 over here, equal in the identity. So we had to go for the smallest integer satisfying that equation. Order of 2.
5.
5. And you see, you can do this for any element in the set, right? Okay. Now, okay, let's do one more example and then we'll move on from there. We have done this, it's a group of permutations here, but I don't think I gave you that name. S3 containing these functions, right? Where X is the set containing only 3 elements. This contains functions where this function is 1 to 1 and on to from X to X, right? And this set, we defined all the functions. F1, we took it to be the identity. F2, F3, F4, F5, F6. And, okay, we defined F2 to be, wait, hold on a second. Right. F2 is chosen so that 1 is mapped to 1, 2 is mapped to 3, and 3 is mapped to 2. And let's take this 5 also. 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. Right. We are going to find the orders of F2 and F5. What is the order of F2? That means, can we find, obviously we can find the orders would be finite because the set is finite, right? The group has a finite number of elements. F1, right? We have to find the least n. Okay, let's go with F2 square. This would mean F2 composite F2. What do we have? When you compose F2 with itself, you see 1 goes to 1 and 1 goes to 1. So 1 has to go to 1. 2 goes to 3 and 3 goes to 2. Now you see that this goes to 3. And this is equal to the identity function F1. So what is the order of F2 in this case? 2. Now let's go to F5. Let's calculate F5 squared, right? This means F5 composite F5. So you have 1 goes to 2 and 2 goes to 3. You know, from the get-go, we know this is not the identity, right? 2 goes to 3 and 3 goes to 1. 3 goes to 1, 1 goes to 2. This is actually, is it? This is not the identity. This is, I think, F6. Now what do? We calculate F5 cube, right? That means F composite, F5 composite F5 composite with F5. Now, this composition we have already gotten here, right? So we look at this one. 1 goes to 2, 2 goes to 1. 2 goes to 3, 3 goes to 2. 3 goes to 3. This is the identity. Therefore, we see that the order of F5 in this case is 3. That is the smallest number that gets to the identity. Okay, do you all have any questions? Okay, now that we know the order, we can do another problem. Okay, let's do this problem. Let G be an abelian group. Now, what I'm just going to use a conventional way to do this. For A, B in G, right? A star B, I will simply denote it by AB for the binary operation star, so that we don't have to write it. Once we understand what the binary operation is, you don't have to just put it over there. When I say AB, this means A star B. So we are going to adopt this convention for this problem, okay? Right, so let G be an abelian group. Let's take H to be a subset of G. We take elements from G such that the order of that element is finite. Order of that element is finite. Okay? And we are going to show that this is a subgroup of G. Okay. Once again, we will use a subgroup criterion to do so. First thing is, we have to show that H is a subset of G and it is not empty, right? H is clearly a subset of G. Why? You take any element from that from the set H, it is an element in G by definition of H, right? So we write clearly H is a subset of G. How do we show that it's not empty? To prove it's not empty, we only have to show that at least one element, just one element exists in the set. How do we show that? Is there an element in the group G with finite order? If so, that element must belong in H. Do we have, for any group G, abelian or not, any group G, do we have at least one element with finite order?
Yes, the identity is there.
Yes, exactly, right? Why? The order of the identity will always be 1. So 1 is a finite number. right? The order of the identity is finite. So we can write, observe that the identity E in G has finite order. Right? It has finite order so that the identity belongs to H. Hence, H is not empty. Hence, H is not empty. Now we have shown that it's a subset. It's a non-empty subset of G, right? Now to use the subgroup criterion, we take any two elements arbitrarily from H. Let A, B be two elements in H. From the definition of this group H, we know that orders of A and B are finite. What does this tell us? Then we must have for some positive integers n and m, let's say, order of A to equal n, order of B to equal m, right? Then for some positive integers, n and m, we must have order of A to equal n and order of B to equal m. This means by definition of the order, so that A raised to the power of n is equal to the identity and Bm is equal to the identity. Okay. Now, what do we have to do? We have to show that AB inverse is in H to use the subgroup criterion, right? To conclude that H is a subgroup of G. We need to show that AB inverse is in H. To show that AB inverse is in H, first we have to show it's an element in G and has finite order. Surely it's an element in G. By A and B are elements in H, so they are elements in G. G is a group, B inverse also belongs in G. G is a group closed under the binary operation, therefore AB inverse is an element in G, right? Now, we have to show that, because it's very clear it's an element in G, we have to show that this element has finite order. That is, we have to show that AB inverse, say, is equal to no, let me put it this way. We had to show that order of AB inverse is finite. This is what we have to show. Right. Okay, now once again, we are going to do some rough work. Okay. If this is finite, right? If this is finite, for some value, for some positive integer, we must have this to be the identity. If this is finite, for some positive r, we must have this to be the identity, right? So this means AR, B inverse R. Once again, from here to here, we use the fact that G is abelian to come from this equation to this one. We use the fact that G is abelian, right? Now, we know for some value, from here we have taken it to be n. For n, a raised to the power of n is the identity. For B inverse, we have nothing so far, right? See what I'm going to do. If we take R to be n times m, if we take R to be n times m, over here we would have a raised to the power of n times m. So we'll take n m, right? And b raised to m n. If we can show, because b, if you take the power of b by m and you get the identity, if you can show that, if we have this also to be satisfied, this equation also to be satisfied, from here you can actually get to this one, right? Sorry. In that case, we can simply take this quantity to be the identity raised to the nth power, which is simply the identity. Identity raised to the nth power, which is the identity, and the identity, exactly what we want. Right? So what is the first step? First step is to establish this equation, and we simply take the product and calculate this and go in this direction. So this is rough. Okay. Now we go back to this. Now what? We take on the left the nth power of B inverse of this equation. So from here we have B inverse M, Bm equals the identity. From here we get B inverse B M. This is simply B inverse raised to the power of n. And this is the identity. Identity raised to the nth power, you get the identity. Exactly what we want. Okay, right. Now, in order to show that this is finite, we calculate the, okay, let me write it separately. We find AB inverse raised to nm power. This you can write as, now in this product, what do we have? AB inverse, AB inverse. How many times? We have nm terms. We do have nm terms, right? Using the fact that G is abelian, we would commute elements so that all these B inverses are grouped together, all the A terms are grouped together using the fact that G is abelian. So we commute the elements to get A up to A or NM, NM terms of A, and then we have B, once again, NM terms of B, right? So we have A, NM, B in, this is B inverse, NM, right? This is equal to, I can simply write it this way, and replacing it by the identity, you have the identity. Is it clear up to this point? Okay. From this, we can conclude So we can conclude the order of this element is less than or equal to nm, a finite number. Why can't we conclude that this is equal to the order? Because we have this equation. Why is that? Since nm is finite, we have order of AB inverse to be finite. So that it actually belongs to the set H. Therefore, by subgroup criterion, H is a subgroup of G. Now, why do we have less than or equal to? Why do we not say equal?
N or M could be the factor of the other one.
N or M could be?
N could be a factor of M or vice versa.
Okay, if it is a factor, what does it mean then? So what does it mean? The order is taken, right? So that whatever value you get over here is the least possible positive value. The least possible. I think that's where you're going with that. When you have a factor of, let's say you can write m as n times whatever, you retain n and you can write it in this form, right? I suppose that's what you were trying to say. So when you define the order, you define it to be the value n such that it's the least n satisfying that corresponding equation. Say for the element the nth power of a equals e. We say that n is the order of a if that is the smallest positive n satisfying that equation. Certainly for nm, the equation is satisfied, but we could have elements that are less than that. We don't know that it is the least value, right? But we do know the order will definitely be either less than this or equal to this one. In any case, this is a finite value, so the order will definitely be greater than 0, right? Greater than 0. So it's a positive value, it's a finite value because it's less than a finite value, right? Therefore, we can conclude the order is finite. By definition of the set, it must belong to H, and the subgroup criterion tells you it must be a subgroup of G.